Hi! So far we have seen categories, which is a good way to describe structure, and we have seen functors, which is the appropriate notion of structure preserving morphism between categories. Now we're going to go up one further level and consider what is the appropriate notion of morphism between functors. So let's say that I have one functor f, which goes from a category C to a category D, say, and I have a functor g of the same type. Now, what is a good notion of a morphism between these two things? Well, f and g here, they are kind of like functions, right? So it makes sense to ask for these things pointwise. That is, for every x, we have f of x, which is an object in D, and we have g of x, which is an object in D. So it makes sense to ask for an eta x, which is a morphism between these two objects. So we usually use eta and tau and letters like this for natural transformations. But that only takes care of the object part, right? So what about the morphisms? So let's say that I have a morphism f from x to y. Then what can I do with this? Well, I certainly have eta x, which goes from fx to gx, and I have eta y, which goes from fy to gy. But now I can complete this square by looking at the action of the functor f on the morphism f that goes from here to here, right? And similarly, I can do the same thing with the functor g. So now I have two possible paths from here to here. I could either go down and then across, or I can go across and then down, right? So it makes sense to ask for these two paths to be the same. That is, I should get the same result if I go left, down and then right, or if I go right and then down. So we say that we're asking for this diagram to commute. The diagram should commute, which just means that these two paths are the same. So this morphism equals that morphism. And this is the notion of a natural transformation. So the eta here is the transformation, and if the diagram commutes, then it's natural. And this is often very useful because you can shuffle the eta past the function, the functor, and that might simplify some further simplifications. So let's see how this looks in Agda. So here is the record for natural transformations. So we see that we have two functors f and g, and we have a transformation which goes from f of x to g of x for every x, and we have a naturality proof which says that for every x, y, and f, if we do this, so this is first mapping, that's going down and then going across at y, should be the same thing as going across at x and then mapping over in g, right? So as an example, let's show that taking the root of a binary tree is actually a natural transformation. So because not all trees have roots, this will have to go into maybe. So here I've just quickly shown that maybe is actually also a functor from set to set. So the action on objects is the maybe type. The action on morphisms does what you expect. If you get nothing, you return nothing. If you get just, then you apply the function. And the proofs of identity on homomorphisms are quite simple, right? So, okay, let's see if we can define this natural transformation that takes the root of a binary tree. Okay, so we have to define two things. We have to give the transformation, and we have to prove that it's natural. So the transformation here, okay, it has to work at every component x, and then at this component, it has to take a tree with values in x to maybe an x, right? So let's take a tree and let's pattern match on the tree. If the tree is a leaf, then we can't give back anything in x, so we have to give back nothing. And if it's a node, then what we should do here by the name of the function and by the specification I gave you is we should just return this x, right? So just x, that's the root of the tree. Okay, so we can transform trees into maybes, but is this operation natural? So let's stop and think. If we go back here, what we see that we need is, I don't know why that happened. What we need is that, so here we have tree of x and we have the root function which gives us a maybe x. So this is root at x. And now if we look at trees of y's, then we have a root of y which maybe gives us a y. And here we have the tree map function applied to some f from x to y. And here we have the maybe map function which sends nothing to nothing and just to just, right? So so now what we're asked to prove is that if we go down and across, that should be the same thing as going across and down. So what does this mean? Well, going down and then across, that means when we go down, we're going to take all the nodes in the tree and we're going to replace them with f applied to that value, right? And then going across, if there is a root, we're going to return it, otherwise we're going to return nothing. Whereas if we go this way, then here we are going to, if there is a root, we're going to return it. And then going down, if it's a just, then we're going to apply f to that value. And if it's a nothing, then we're just going to return nothing. So we see that if we start with a nothing, then we're going to, over here, then we're going to end up, sorry, if we start with a leaf over here, then we're going to end up with a nothing here. And if we start with a node, then we're going to end up with just of f of x here. So it seems like no matter which path we go, we're always going to end up with the same thing. So let's see if we can also make that work in the code. Okay, so something has happened here. Okay, so get given an x, and a y, and an f. And we have to show that these two functions are the same. So we use function extensionality to show that. Which we usually have to do for these proofs. Okay, so we get given a t. And now we have to show that if we first map and then transform, that should be the same thing as first transforming and then mapping, right? So this is the map of maybe. Okay, so let's do this by looking at the t. So this t is either a leaf or a node. Okay, so if it's a leaf, then we get nothing no matter which path we go. So we can prove that with REFL. And if it's not a leaf, then here we are first going, if we transform first, then we take the x and put it in just. And then the map will apply f to it. Otherwise, we're going to apply f to it and then put that in a just. But the end result is always going to be just f of x in any case. So that always works. Okay, so that's quite a down-to-earth example of a natural transformation, right? And there's lots of examples like this. So whenever you have parametric types, most things you can think of are actually natural, which I guess is a good thing.